Okay, welcome everyone. Welcome to this session, which is actually the second session during CPDP, where we dedicate a workshop type to privacy-enhancing technologies. And this year we'll be zooming in on privacy machine learning in combination with pets. So the privacy machine learning, or Ppml, is a very broad and complex field. So the main takeaway today for you will be to learn on how to engage with technologists, with people with an engineering background, to ask good questions. So the speakers, and I'm going to introduce the four to you quite shortly, have been instructed to create a really great presentation for you, and making sure there are no mathematical formulas, trying to explain this in an easy to understand way, but obviously that's a challenge. So this workshop is also intended to be interactive. There is a mic here. The session will be recorded, so if you have a question, please use the mic, or otherwise we will repeat the question. So today we prepared two practical topics around machine learning. The first one will touch on auditing bias in the machine learning systems, and basically how do you actually do that? Because from the legal perspective we hear about these requirements, but what does this actually look like doing an audit? And in the second session we zoom in on mitigating and auditing privacy risks in machine learning, and what tools do data scientists have to explain risks. And one risk that stands out today is membership inference risk. So the four speakers will co-present, and we will hear in the first session from Lindsay, Carignan and Nigel Kingsman, and the second one by Victor Ruehle and Reza Shokri. So let me introduce Lindsay first. Lindsay is the head of customer success at Holistic AI, and has her law degree from North Carolina Central University. And an interesting fun fact about Lindsay is that she has fostered nearly 40 animals in the last 2 years. Nigel, colleague at Holistic AI, is the AI insurance lead and has a Master of Science in Machine Learning and Mathematics. And he's a black belt kickboxer, so welcome. Victor Ruehle, maybe you can wave your hand. He is the research manager at Microsoft, bridging across privacy-preserving machine learning research, product and policy. And he likes to work outside. He's an enthusiastic hobby cook and gardener. And Reza Shokri, and I'm actually very pleased that he is here with us today because he traveled all the way from Singapore. He is an Asian Young Scientist Fellow and at the National University of Singapore, a Presidential Young Professor of Computer Science. And he's working on data privacy and trustworthy machine learning. And the fun fact about Reza is that he loves gardening as well, so that's what you two have in common. And he's growing actually a forest on his balcony. Well, if you would explain this in Amsterdam, this would raise questions, what you're actually growing there. But anyways, we're very grateful that you're all here with us today. And with that, I give the floor to Lindsay.
Thank you. I appreciate being introduced as somebody who's fostered 40 animals rather than a crazy cat lady, but I'll take either. So my name is Lindsay Carignan. I'm our head of customer success at Holistic AI. And a little bit of background on what we do at Holistic AI is we're helping companies adopt AI with trust and confidence. And what that means in practice is doing assessments like bias audits, but also looking at other factors as well, to try and make sure that they're reducing the risk of adopting the technology. So here today we're going to talk about AI risk management in the auditing bias. And it's first we have to define bias. So what do we mean by bias? And that is looking at the risk that the system treats individuals or groups unfairly. So for this, we have machine learning can be used in critical applications like recruitment or the judicial system. And we see that in legislation that is currently out, like the New York City Local Law 144, as well as proposed legislation in places like California, New Jersey, New York, and the EU AI Act. And in these cases, it's especially important to ensure that algorithms do not discriminate and instead treat everyone equally. So I'm going to turn it over to Nigel.
Thank you, Lindsay. My name is Nigel Kingsman, already introduced. I can't really follow up on a mad cat lady comment, so sorry about that. But let's continue. So, what do we mean? What causes AI bias? So, AI systems can exhibit bias due to a number of reasons. The one that comes up most often actually is normally just a case of kind of garbage in, garbage out. So if you are giving your AI training system a poor set of data which has bias already built into it, unless you take deliberate action to prevent that bias going through into your machine learning system, that bias is going to continue to be there afterwards. Otherwise, there's also just using a poor training pipeline. So there's lots of things you can do on the way to creating your AI system, and there are methods that can be employed to decrease bias on the way. But there can be also things such as just making sure that you're collecting samples correctly, you're using the correct kind of targets in your training to help your pipeline generate a better model. But also something that's often overlooked as well with regards to AI bias is actually how accessible is a system. So one of the things that we look at in holistic AI and something that we ask about when we assess systems is, depending on what the use case of the system is, can everybody use it? So for example, if you're rolling out, say, a recruitment tool, and that's being rolled out globally, then assuming that people have got, say, a high-powered laptop in order to be able to put in their application is a massive assumption, and it actually discriminates against those who don't have that availability. So next slide. So is that moving? No, that's a pointer. There we go. Thank you. So how do we look at bias? How do we assess it? So the way holistic AI approaches this task is we very much treat it as a cycle. So where we start is that we take a look at the system when it gets onboarded onto our platform, and we perform an assessment over that system. Now, I'll detail a bit more on that assessment, but it comes in two parts. One, we actually have a qualitative aspect, and two, we have a quantitative aspect. This assessment then generates reporting. We provide that reporting to our clients. That reporting includes next steps for our clients. And the idea is that the clients then have something that they can then take away. And then if they perform that, then it can help their system become less biased. And then the step that naturally follows on from that is the mitigation step, where our clients perform that before we go through this cycle again. So what does assessment look like? So our qualitative assessment, the way we perform it, is that we ask a number of questions. Now, curiously, the first question that we ask is, have you thought about bias at all? Which sounds fairly obvious, but actually some system owners just simply haven't. And if they haven't, then we really are starting from the very, very first step. And sometimes there's a real kind of hand-holding exercise that has to take place. But once we've got past that step, then we ask about a number of things. So we ask about data. So I've alluded to that already, but we're really keen to understand things like the balance of the data set, whether the data set is representative of the use case and the user population who will be using the system. We ask if they've considered it, what sensitive attributes that they're looking at and what they care about. We ask about any bias metrics that they've brought to bear to try and measure and get a quantitative feel for what bias might look like in their system. We also ask whether they've used any techniques to try to take away the bias that might be present in their system. And lastly, we ask about monitoring. Are they watching it? Do they have a process in place? And do they have procedures in place to check to see whether, even though there may not be bias in the system today, could there be bias in the system tomorrow? And lastly, as already mentioned, we consider accessibility. So that can be, I've mentioned like high-powered laptops, for example. It can also be along the lines of, does your interface, for example, does it use words? that some users are simply not going to understand, certainly if you're assuming that everyone using it is, say, operating in English? Or does it discriminate people who have colour blindness, for example? I.e., does it adhere to good kind of web design? So following asking those questions, we then perform a quantitative analysis. Now, typically, we can get away with just getting data from the client. So if we get some idea about how the system makes its predictions, and we've got some idea about what the ground truth labels are of the data set, then we can do some computation over that information, and we can compute values for a number of bias measures. Also, we can, if the clients are willing to allow us to have access to it, we can get access to the model as well, in which case we have the opportunity to fire a wider data set at the model and see how it performs across the full spectrum of possible samples. Now, one thing I'm keen to mention here is there's effectively two main paradigms of bias. There's equality of outcome, and something I'll come to, which is equality of opportunity. Now, equality of outcome is really just looking at the predictions that your system makes. So it's effectively saying, if you're, say, looking at discrimination between, say, males and females in, say, a recruitment context, you're looking to try and ascertain whether the number of positive outcomes for males as a percentage of the male applicants matches the percentage of positive outcomes for the female applicants as a percentage of those female applicants. So really, you don't care, per se, whether the applicants should have got the job. You're just making sure that the same percentages for both males and females get offered the job, right? So that's equality of outcome. And the standard metrics that you might see around for those are disparate impact and statistical parity. And in fact, a version of disparate impact is used by the New York City Local Law 144. The other paradigm is equality of opportunity. So equality of opportunity is where you then condition upon some aspect of the candidates in our example. So for example, the best one to condition over is if you actually have the ground truth label. So the ground truth label would be, should this person, under say human review, should this person get offered a job? And then you're looking to see, okay, is the percentage of males who should be offered the job given say their qualifications match the percentage of females who get offered the job given their qualifications. So you're conditioning your assessment of equality based on some other feature. You're not just looking at outright success percentages. Sorry? Apologies. Okay. So standard metrics that we use for this are equal opportunity difference and average odds difference, and they are just both conditioned kind of mathematical approaches to the calculation. Now, what do we have to think about? When we're looking at bias and reducing bias in the system doesn't come for free. So minimizing bias exhibited by a system, although I'm sure we can all agree is a good thing, it's not for free. So one of the things that you typically might have to give up in order to ensure that your system is free of bias, or at least exhibiting less bias, is system performance, what we call efficacy. Another thing that you might have to give up is some level of privacy. So, for example, you would have to, if you really want to ensure that your system is free of bias, then you will have to have some idea of some of the sensitive attributes, say, of, let's say, the candidate base, in order to check that it really is free of bias against those attributes. And curiously, the other thing that bias sometimes has to be traded off against is other measures of bias. So this is where you have many, because there's so many formulations of bias, and I've already mentioned the two distinct paradigms, but within each paradigm there are about 50 different measures of bias that are out there within the research sphere, and it is possible to seek to tackle bias using all those measures. But I'll break these down a little bit more. So when we come to looking at the trade-off against system performance, where data exhibits bias, debiasing can lead to decreased accuracy or increased error rate of your system. Just to kind of show what I mean, the top right chart there shows how the error rate on the horizontal axis, that goes up as the disparate mistreatment measure decreases. So as we go from a bias measure of 0.1 down to 0.0, you can see that the error rate is increasing from 16% to 19.5%. So your system just isn't being as accurate as it would have been before. Typically, the performance of the system over the privileged group, let's say males, is negatively impacted during debiasing to converge with the non-privileged group's performance. So, for example, if the success rate for females, say, for going through to interview is, say, 50%, and the success rate for males is 60%, debiasing techniques can often force that male rate down to 50%. So it's actually just making instead of bringing them up to maybe an equal level of 55, which would be, where you would hope it would go to, you're actually just seeing one group being kind of comparatively disadvantaged to bring it to equal. And then on privacy. So I've mentioned this already. When we consider the bias that might be shown by the system, we need to collect the relevant sensitive attributes for both measuring the bias, so just to know, is it biased, but also we need the sensitive attributes so we can use that as part of our mechanisms to reduce bias. So as such, greater data collection is needed in order to tackle bias concerns around a system, and that of course increases privacy risk, because now your data, if it gets out into the ether, is far, far more sensitive, and it's far more powerful for a bad actor who gets hold of that data. And lastly, we talk about conflicts between bias measures. Now, I'm not too sure how easy that chart presented here is to read, but effectively what it's trying to convey is as you improve one bias measure, another bias measure gets worse. This isn't always the case. It depends on which bias measures you use. But the point I really, really am keen to make here is with AI systems having so many stakeholders and with the media getting more and more involved in the AI systems debate, the risk is that there's going to be more and more demand across very, very different bias metrics and bias measures for a system to be free of bias. And not all of these can be done at the same time. So the next stage of our cycle is reporting. So what does reporting look like? So at Holistic AI, we have these two concepts of risk. We have a concept called inherent risk, and we have a concept called residual risk. Now, inherent risk is the risk that we see a system as having in the absence of technical mitigations and robust procedures being in place to control for that risk. Residual risk is what we see when those things are in place. So there are mitigations in place of a technical nature, but there are also procedures in place to control for those risks. And what we try to do when we report to our clients concerning their system, we surface to them what we understand the inherent risks to be, and we surface to them what we understand the residual risks to be, given what we know about their procedures and their technical mitigations that are in place. Now, the big aim that we want to get to, ideally, is to have residual risks as being low across the board. So we don't just look at bias, as you can see here, we look at other risks as well. But with regards to bias, if a system comes in having a high risk, in a perfect world, by the time we finally report to a client, it will be a low-risk system, because we will be confident that they've got suitable controls and procedures in place to cover that. Also, as part of our reporting, where we see that there's some outstanding bias risk, we will actually make requests of our clients. And those requests will be in an effort for them to put in procedures and technical mitigations to bring that risk down to low. And this all forms part of the cycle. So ideally, and we'll come to mitigation, if they perform those actions, then we can revisit the system. And hopefully, if those actions have taken effect appropriately, then we'll be able to revisit the bias and hopefully get it down to a low risk. So this brings me through to the last part of the cycle. That's mitigation. Here we know that in general, machine learning systems are trained with an objective of minimizing a loss function for that system. Hold on, my PowerPoint's mucking around a bit here. Making the minimization of bias being part of that system requires a change to the machine learning model. So typically, the algorithm is trying to maybe ensure that accuracy of the system is as high as possible, and that will be the model, and it's being trained that way. To minimize bias, you've got to change the pipeline somewhere. So how can we change the pipeline? There's 3 places where we can change that pipeline. We can change it before the data is passed to the model. This stage is called pre-processing. We can do it at the time of training the model, whilst the actual number crunching is taking place, or we can do it after the model is trained. Now, breaking these things down further, so in pre-processing, that's the one that's kind of probably easiest to relate to, and certainly where your data set is, sorry, I should have skipped forward, certainly where your data set is biased already, pre-processing is a very, very good first step. So with pre-processing, you could say, for example, oversample some of your data. So let's say you've got a minority group in your data that's not very well represented in your data set. You can oversample them so that the balance between the kind of majority classes in your data set and the minority classes in your data set gets far more equal. What's the advantage of doing this? The advantage of doing this is that when your model, your training algorithm then sees the data, it will see that minority part of the data set as being equally as important to ensure accuracy over as the majority part of the data set. Whereas before, it really gave, overbearing weight to just making sure that the majority piece was performing well. Meanwhile, in processing means fundamentally changing the algorithm that you're using to build your model. So what this means is that you might say bring in a constraint, to say, look, only train the model in such a way that bias is within certain bounds. Or it might have another constraint to ensure that, to an extent, the success rate for, say, male and the success rate for female are only allowed to get so far apart at each stage of the training. So that's an expensive way of doing it, because obviously you're having to retrain the model from scratch, and if the model costs an awful lot of money to train in the first place, and you're going to have to do that again. But the same is also true of pre-processing, because you've got to change the input data. Post-processing, however, is very different. Post-processing, you're attempting to get a less biased system without having to change your input data and without having to retrain the model. So that is the cheapest way of doing it, but it might not be the most effective way of doing it. So there's decisions to be made by your data scientists in order to determine which mechanism is best. Okay, and I'll pass you back on to Lindsay.
Thank you, Nigel. Have we lost our... There we go. So when we look at the limitations of bias, there are a few things to look at. So we were talking about the availability of the sensitive attributes, and that is not just from whether you're collecting the data to begin with, but also how often people are actually putting that input in, even if you are collecting it. So usually it is an optional for the participants, for the people that you're collecting the data for, to give that data. Things like GDPR, I think Germany, it's prohibited from collecting those kind of attributes, make it really difficult to have the information to begin with. And for things like the New York City legislation, when we're looking at data sets from vendors, I mean, oftentimes, I think, some of the highest we've seen is like 20% of the population that they're giving us has that data, but often it can even be under 1% of the total population that is going through their system that has these kinds of sensitive attributes. Then when we look at things like the data size, the data set size, that can also be challenging, especially when we look at the intersectionality. So if you're looking at male, female, that tends to be data that we get more often. And then you start seeing drop off when it comes to the ethnicity. And then if you're trying to say, you know, a Black female that's over 40 is going to be significantly reduced. In the US with things like the EEOC categories, I mean, you're also looking at how much of the population is there to begin with. So for, you know, Native American population, for Pacific Islander and Hawaiian, in all of the data sets that we've seen have been under a 2% sample size, which isn't enough to give us any information that's statistically significant. And then one of the other limitations around a bias assessment is the narrow focus. So we're just looking at bias, and when Nigel was talking about the other types of assessments that we do at Holistic AI, it's a trade-off. So if you're looking at just bias, you might not be looking at efficacy, you might not be looking at privacy, you might not be looking at the robustness of the model. And then he did mention as well the exclusivity of the bias metrics. So there is a trade-off when you're looking at bias metrics. You can't optimize all of them at the same time. So it's important to have questions that you can ask your data scientist. So we wanted to give you some that, you know, to put in your toolkit. What is the provenance of the data? So where does the data come from? How representative is the data? So that is, you know, if you have, you know, the population is 50% white, does that look like that in your data set? Is it proportionate to the population? Is the data set balanced? So that is more on the mechanism that you're using around the data. So if you're looking at scores, are the score categories that you have representative in the data set as what you actually see total? The intersectionality, is it being considered? So one of the things that we've seen in New York is that they did end up looking at the intersectionality, which is good. They, as the final version, they didn't start out that way. So initially it was just looking at, you know, male, female, the ethnicity is all separate, but the intersectionality is important, and often where you see more of the bias is at the intersectionality level. And depending on how it's calculated, can be compounded at the intersectionality level as well. And then are sensitive attributes present in the data at all? So is it something that you're collecting? And as Nigel mentioned, you know, when we ask, are you looking at bias? You know, there are some that don't have any model to begin with. And there are some that we've spoken to where it's like, well, we don't collect the data, so it's not biased because it's not being used in our model. And as we talked about the outcomes, that's not always it's not exactly how bias works. I did see a lot of people taking screenshots. I do manage our chat for Holistic AI, so if you do want to pop your name and email in there, I'm happy to email you the presentation as well after to make it easier. I think we're going to take one or two questions.
Yeah, thank you very much. This is your moment to ask clarifying questions or follow-ups. If not, I have a few questions prepared. Yeah, go ahead. Please speak into the mic.
Thank you so much for this. Can I hear me? Can you hear me? Yes. Okay. Yeah. So this is really illuminating. I'm very curious about this meta settlement with the FTC in the States, and sort of about having to debias ads in housing and credit scoring and things like that. And so my understanding from your presentation is that the solution that is being proposed there is this variance reduction system, which I'm understanding, you know, with what you laid out as a post-processing system, and you said, you know, there may be sort of limitations to that. So I have sort of only a superficial understanding of what can be achieved there, and I'm curious, like, if you, you know, again, just like sort of plugging it into the framework you laid out, if you could maybe give me your impression of like how workable is this, or what is being achieved, you know, with like a VRS system, and what maybe can't be achieved. And then on top of that, like, you know, making this work in maybe a European context where a category like race, which is really, you know, defined one way maybe in the States, is a bit trickier in Europe. Yeah.
Yeah, sorry, that's loud. I can try and talk to that a bit. So realistically, post-processing techniques, if it was meta that you're talking about, right? So there'll be something that they can do, but if they don't want to be spending too much money on going through the retraining cycle, and I'm not I haven't looked into this particular case, so I don't know how heavy that system is, but if it is heavy, then it might be prohibitive for them to come up with a whole new model from scratch. No, so post-processing techniques do work. They can work. They don't necessarily work, but really, in the absence of actually seeing how they're getting on with doing that, I can't certainly comment. But there will certainly be cases where the nature of the model and the nature of the predictions that it generates will actually make it near impossible for post-processing to certainly work. So mathematically, there'll be times when it just can't happen. And if they're limiting themselves to that, then obviously they're leaving a lot of opportunities in the toolkit. But this is unfortunately a risk around large models. I mean, certainly like with the big language models, I mean, if someone asks you to retrain that, then you're staring at a very, very big electricity bill and a lot of time. So yeah, it's a tricky one, but I think it will help. But I think they're leaving a lot on the table with that. Does that help?
And then I think the second part was about race and ethnicity in regards to Europe, where it's viewed a little bit differently. So I think if we look at the context that we were talking about, so we've got the opportunity of outcome or equality of opportunity and equality of outcome. So equality of outcome is what we're looking at with legislation like New York. So we're using the impact ratios, which is a form of disparate impact based off of the races. Things like the EU AI Act is much more about opportunity. There is some on the outcome, but it's much more focused on what are the processes you have in place, at each of those stages. So the pre-processing in the middle, and then at the end, to try to reduce the bias along the way. So it is looking at race differently from that perspective. And it's not just about race, it's gender. And then things like even in the US, it's going beyond race and ethnicity and gender, and saying, we're doing the whole gamut. We're looking at disability. We're looking at not just like gender, sex. It's, are you, is it your status as a pregnant woman? Does that help?
It does help, thank you.
Hi, good morning. And I have just a question regarding if the system would also be possible to apply to black box that's in deep learning systems, and it would be possible in processing, modifying the algorithm, and if it yes, how does it work, specifically in the medical device? I don't know if you have already tried to use it into the medical devices. Thank you.
That's a good question. So the pre-processing and post-processing techniques are kind of agnostic about the nature of the model itself. But the in-processing techniques, that's where things get a bit tricky with neural nets. So a lot of the in-processing mechanisms are based on, I can't remember the terminology now, but kind of standard minimizers. And they'll be for usually the traditional machine learning models, not the deep machine learning models. Saying that, there are some techniques that you can apply. It's just that with neural nets, you're far more constrained as to what you can do. But you can still add certain extra constraints into your model learning cycle in order to achieve different kinds of behavior. Cool.
So I have a question as well, and then I hand it to you. Yes. So from where you are sitting, why are companies seeking out to do bias audits to begin with?
So I think really there's a few different reasons. Compliance being the easiest target. So we've got the legislation in New York, the EEOC, and a number of federal organizations have come out saying that they're using existing legislation to enforce the same kind of measurements in AI. The EU AI Act is set to be voted on next month. and then will likely come into force in 2015. But I think more broadly than that, there is an upsurge of companies trying to be ethical, be responsible, and employ ethical and responsible AI. And I think there's a push from, society. I think you see it in Gen Z, especially when you look at some of the studies and metrics around how they're choosing companies. It is monetarily driven by organizations as well if they're wanting to maintain their consumer base, that they do need to be ethical and responsible for people to want to put their money into their products.
Okay, final question from you.
Maybe a very practical question. So like imagine you have a company, and then they have a process, and then suddenly somebody decided to do it with AI. So they downloaded some open source stuff, and then created a model. And then they decided to do this analysis, so discovered some biases, so they have to retrain or whatever. So according to your experience, how the company notifies users who are already maybe in a contract with the company, how they notify people when they introduce the model, so to which degree of detail, what they will be doing with the data using AI. And after that, when you have done the analysis and they need to debias that, it's a kind of like going to the user and telling, by the way, we made a mistake, so now we are correcting. So what do companies communicate to users in terms of correction?
Sorry for that.
So usually, at least the releases that I've seen for that is more we are using your data, to uphold law and for legal restrictions, and that they don't necessarily need to be updating the users if they're then trying to do something like an audit to comply, especially with regulations and legislation. I think part of your question was around if they're updating essentially the model after the fact, if they found bias, like what obligations they have. And at least from what I am aware, which doesn't mean that there aren't any, legal requirements or regulations, because I am coming at this from the head of customer success, but I don't think that there are necessarily any requirements that they do share that. There may be some agreements that organizations have with their vendor, like a vendor client, that if they're releasing a new model, they need to be aware that a new model is being introduced. But I would suspect that the reason for introducing the new model wouldn't be disclosed.
But if you talk about, let's say, risk models, for loan, so they have declined a couple of customers, and you go in, you say, oh my God, the model was wrong, you correct the model, and most likely some of the customers would have gotten a loan under the new model, so you need to kind of tell users that we have updated the brain behind it.
Again, I think you might want to lobby for laws that make people disclose it. There may be people in the audience who have more visibility in that than I do, but at least from the wide news and what I know, I don't think that there is a requirement to necessarily disclose that.
Well, thank you very much. We're wrapping up this first part, and now it's up for Victor and Reza for the second half. Thank you very much. Thank you.
So thanks for the great presentation. So in this part, Reza and I will zoom in a bit more on the privacy side of things, and particularly about mitigating and auditing or measuring privacy risks in AI systems. And I'll quickly wait for the slides to come up. Oh, perfect, thanks, So, and particularly what we're going to do is focus on the measuring aspect, and we think it's an emerging technology in research, but we think it really can help to bridge between technology and some of the regulatory concepts. So
So we'll first talk about leveraging private data AIs, the opportunities, risk, and mitigation. And then in the second part, Reza will talk about how do we actually quantify information leakage and how do we visualize and communicate privacy risks based on some examples. What we would like you to take away from this session is that privacy violations in machine learning can be very subtle and unexpected. So we need privacy auditing tools to accurately measure the privacy risk and compare effectiveness when applying different privacy enhancing technologies. So we have that tool in the form of membership inferencing, and this can provide an intuitive solution to understand and communicate privacy risks, and then also which is associated with machine learning algorithms. And lastly, we think that these tools can help to balance privacy and utility of these models and ensure we can fulfill regulatory compliance. So I'm sure all of you are aware about the opportunities of training machine learning models on private data. So if we leverage private data to train these models, they can unlock unprecedented AI capabilities in healthcare, social justice, or financial services. For example, fine-tuning a model on private medical data, researchers were able to create an experience, created a system which helped to identify onset of an eye disease very accurately. In social justice, by training on social media data, private social media data, you can create a system which helps to predict suicide risks. Or in financial services, by leveraging private financial transaction data, you can build systems for fraud detection. So there's definitely a big value proposition, but we need to balance the value proposition with privacy risks. So we have regulatory requirements to ensure we do these systems in a privacy-preserving way, and GDPR generally requires anonymization or pseudonymization of private data to minimize the risk of re-identification. We have a whole framework of requirements around data collection, data processing, the necessity and proportionality, and the threat impact assessment on the threat of individuals. So we require implementing technical and organizational measures to ensure the security of the private data. And the technology we're going to talk about today can be an important component in this framework to essentially identify and analyze possible risks and mitigations and how to continuously monitor them. So let's talk a bit more about privacy threats in machine learning. So generally, we can have multiple types of risks. For example, there can be leaking of personal data. I'll give an example a bit later. Or there can be the risk of re-identification of an individual. So can I tell if I used the data of a particular individual for training an AI model which would violate singling out? Then this risk can materialize in just normal use. By a legitimate user might interact with an AI system, and you might reveal some sensitive attributes from individuals. Or it could be an attacker actively trying to interact with a system, trying to infer something about the private data which has been used to train this model. Another thing is like the adversarial capabilities really depend on how I deploy the model. If I deploy the model in a cloud API and give limited access, a potential attacker has less capability than if it would ship the model on device and have uncontrolled and full access to the model. And again, the tools we present can incorporate this amount of exposure to make a judgment about this. So these risks are not theoretical risks, but they exist not only in machine learning, but also in releasing aggregate statistics. For example, the risk of re-identification. The example we picked out here is where publishing of average statistics about genome data with a group with cancer and without cancer, an adversary could tell essentially if a person's data was used in this aggregate statistics. Not only if it was used, but also if it was in the group with cancer or without cancer, which is obviously a huge risk. Now, aggregated statistics are fewer parameters, much lower dimensional than some of the machine learning models, which are much more complex. And this is, has been shown in various research work that text generative models, for example, can memorize phone numbers and addresses of individuals and then reveal them at inferencing time. Now,
sorry, would it be possible to download the slides afterwards or receive the slides?
yes, oh, yeah, yeah, absolutely. Let's connect after the talk and I'll give it to you. It's interesting to know that larger models, if we don't mitigate the risk, have increasing capabilities to remember rare training sequences and then leak them at inferencing time. And also the model size versus the amount of training data we have impacts the risk in terms of overfitting. On a good note, we have very effective tools if we're careful to mitigate this risk and still get good things out of the model, but we do have to apply risk mitigations for here. So we have, to mitigate this risk, we have privacy-enhancing technologies. And there's a lot of confusion, what technology should we apply in which case. Here, I've generally categorized it into two groups. On the one side is, what do we reveal about the data which mitigates the risk when we publish results using these models? And techniques in this group is, for example, differential privacy, de-identification methods like PII scrubbing. And we can apply not only one of them, but we can apply multiple of them depending on the risk level of our application. Then also, if we apply privacy auditing, we might want to go back and revisit what type of methods we apply and make it stronger or maybe increase the utility of the model. On the other side, we have technologies which are, how do we process the data, which limits the access when we process the data, when we train these models. And that is, for example, federated learning, to keep data in silos, cryptographic technologies to limit access and that we won't be able to access it, but they won't mitigate the risk when we essentially publish results from the model. And typically we combine multiple technologies out of both groups to achieve the desired effect. To zoom in a bit more on one particular technology, which is probably the industry standard for mitigating privacy risk, is the differential privacy. So the goal of differential privacy is it enables model training on private data of many participants by concealing the presence of any single party and ensuring that only general trends about the data is exposed. Differential privacy achieves this by adding noise, which will have a negative impact on the utility. Also, there's parameters I need to tune, and these parameters are very hard to understand by non-technical people, and it's not obvious how to choose them. And lastly, differential privacy, the parameters provide me a worst case bound, and they not necessarily reflect the real risk of my application. Well, not necessarily, they do not reflect the real risk of my application. So there's no silver bullet, no free lunch, and mitigating model leakage generally comes at a cost of utility. And deployed AI models require layering of many solutions. As a rule of thumb, it's a good practice to apply the least disclosure principle. For example, even if you apply differential privacy and we don't need full access to the model, but we can put it behind an API endpoint and, for example, throttle the API, combining these effects is a good practice. Now, the question arising from this is, how do we talk about combining privacy-enhancing technologies in a cohesive way and enable quantitative comparison? And that's what Reza is going to talk about now.
So what do we mean when we talk about data privacy? What do we mean when we talk about privacy risks or information leakage of an algorithm about its individual data records? How can we quantify that? We want to put numbers, we want to measure them. How can we design algorithms to actually do this
quantification for us. And moving towards standardizing this whole process, can we design tools that actually practitioners use to do these privacy risk assessments in a reliable and precise way? So these are the kind of questions that we want to address. As mentioned before, machine learning algorithms can unintentionally leak information about their training data. This is a very subtle risk. It's an indirect information leakage. No adversary has direct access to the training data. A user, a legitimate user of a system, has access to the model parameters or the predictions of the model. We want the users to have access to those information, but the same user could be very curious and try to extract information about the training data. We want to prevent that information, the detailed information about individual data records to be communicated. So we need to be able to quantify that. And this goes beyond the procedural auditing of privacy and requires looking at the bits of information which is leaked. So for this, we design a game. We design a game, we call it membership inference. So the way that it works is that imagine that there are two worlds, two parallel worlds. In one of them, your data is in the training set, and in the other one, the rest of the data is there, but your data is removed. Okay, so the only difference between them is that in these two worlds, your data is one of the training sets and the other one is not. So we randomly pick one of these two worlds, train the model, and show the model to a hypothetical adversary. Ask the adversary if he can detect in which world he is in. If there exists an algorithm that simulates an adversary that can tell in which world he is in, the reason that he would succeed is that the algorithm leaks information about your data. Otherwise, it wouldn't be able to distinguish the two worlds, okay? So we admit that the success rate of such a hypothetical adversary is a very good measure of information leakage about individual data records in the training set, right? So how do we design this? How do we design these algorithms? How can we simulate an adversary in order to quantify privacy risks? I'm going to, at a high level, present what the gist of the idea is. So there is a data universe, and there are personal data. There are personal data in the whole universe, right? And we know when we train a machine learning algorithm, we sample from this universe, kind of we partition it into the training data and the rest of the data that we don't have access to. We train a model, adversary observes the model. Now he wants to know whether a data point is there. He has to reverse the process. He uses some algorithm to project the data into some one-dimensional sphere and then partition the data. Say the ones who are on the, let's say, your left are the training data, that is his inference, and the other ones are not, right? He is going to, for any partitioning that he comes up with, he is going to make some mistakes, and he's going to identify certain data points correctly. So he has an error, a false alarm, and also an accuracy. This gives a point about the performance of that attack. Now, if you go over all different ways that the adversary can partition the space, you get this nice curve. That is, every point in this curve is corresponding to a particular adversary who would partition the space into members and non-members. And for the cases that he partitions into members, he is correct for some of them and incorrect for the other ones. If the profile, if this curve is towards the up left, there is a huge information leakage. It means that the adversary is able to identify which data points are in the training set. He is going to succeed in his re-identification attack without incurring much error, right? So some of you are part of some group. I'm going to identify some as members and miss some other ones, right? This is how much my correctness in identifying the members is something this is reflected in this profile. So we can actually design tools that enable us to quantify this risk in an automated manner, right? That's interesting data projection that I showed requires some sophisticated information theoretical algorithms. And but tools exist. There's a very popular open source tool that enables you to measure and quantify the privacy risk of the algorithm and generate that privacy risk profiles. Okay? Why are these useful? So it's useful because it enables you to move towards a standardizing privacy risk, as opposed to everyone is talking about different types of risk and threats, and numbers might not match, right? And number two, can help us to move towards a transparent privacy auditing. So when we talk about privacy auditing, we know what we're talking about. There's an open source tool, and the algorithms for measuring privacy risk can improve in order to provide a more precise measure of the risk. And in this ecosystem, we can enable that. So this is the profile. And what is very nice about this profile? So this profile is what is reported to the users. What is good about this is that actually we can partition the space where this curve can happen into low risk, medium risk, and high risk, based on what kind of attacks could be successful there, what fraction of the data points an adversary could reconstruct, what kind of sensitive attributes about the data he can reconstruct, and so on and so forth, which enables the practitioners to take proper actions as a result of this privacy risk. So you don't have to really understand what happens if this curve changes a little bit. All you need to care about is whether you are in the green area or you cross to the red area. Okay? And to give you a little bit of insight about, again, what this curve means, when you move towards the left, it means that the adversary is able to single out individuals. Okay? That's an adversary who is very conservative, says, I want to find any individuals that are in that training set, reconstruct the information about any individuals in that training set, and I want to be very precise about them. Okay? I'm going to miss some other data points which are in the training set, but the ones that I reconstruct, I'm very precise. I'm singling out. That's the risk of singling out. As you move towards the right, the adversary's objective is, I want to recover as many training data points as possible, even though I'm going to make errors and have some other random data points from the population that I falsely believe are in the training set. Okay? These are all different types of risks, and that influences how we design and define these regions. So let's go through a particular example that helps us understand the whole auditing, and that is the example of an NLP classification task. So language models memorize a ton of information about their training data, verbatim. So you can reconstruct a whole lot of information about the exact sentences that were in the training set, right? When we measure the privacy risk of language models, all different types of language models, you see that the curve is almost close to the maximum risk, right? It's very covering all the red area, right? You remember that when it goes up left, it means that the leakage is large. When it goes down, then the leakage, when it is on this dashed line, if it happened to be on that dashed line, means that the adversary has no clue which data point is in the training set, which data point is not. But when it goes up there, it means that he's very precise on a large fraction of the training data points and what their values are. So without any privacy-enhancing technologies, we are doomed on language models. And large models in general, they memorize a lot. But we have a lot of techniques out there. Some heuristics, some more sophisticated. We can do PII scrubbing. We can use randomization algorithms for differential privacy, and so on and so forth. Okay? What privacy meter and in general privacy auditing technologies would enable us to do is to just say how these different privacy enhancing technologies perform in practice. on the data that I have, right? Because depending on the distribution of the data that you have, certain algorithm will perform better and worse compared to the other data. So how do we do this? Let's say, for example, we do PII scrubbing and then train a model on that. So we see that, well, the privacy risk has decreased. We have moved down. It means that now there are a number of data points that were singled out. That has reduced significantly. Okay, but still we are in the red region. The risk is not negligible. Now we add some randomness to the algorithm with the differential privacy guarantee, which is a mathematical guarantee for privacy. And whoops, then we see that actually we got very close to the perfect privacy. The privacy risk has reduced significantly, but of course at some cost of utility, as mentioned before. Okay, but then you can handle how much randomness I want to add, how much privacy I get for that, how much utility I lose. So this quantitative measure of privacy enables us to do that. And by the way, to add to this is that differential privacy nicely fits in this diagram. This is the bound for a differential privacy mechanism that led to this much privacy loss. So what differential privacy says is that there exists no adversary whatsoever who can get this green curve above the black curve. Which means that it's guaranteed that, for example, you don't cross the medium risk region. But because it's a privacy bound, it could be loose. It could be that you can never reach that on the data that you have. In the worst data set, in the worst day of our lives, maybe we get there, but there's no adversary that can get it above that. So to conclude, basically, we want to bridge the gap between descriptions of privacy risks and quantifications of privacy risks. Okay? Privacy could not be quantified completely what we presented, but it's necessary to be used for quantifying privacy risks. Okay? This enables us to accurately measure, compare different techniques, and you can come up with a proof, right? So some of the people that actually, companies that use the tool, they do it because they want to have a proof that they did their best to mitigate the privacy risk of their machine learning algorithms. So you can compare now in a fair way, right? It's not that your technique is measured in number of apples, my technique is measured in number of oranges. No, it's like one single metric. And it helps with balancing utility and privacy. What is very interesting, and the question for you is, how do we move towards a comprehensive privacy auditing framework when we look at we take into account the procedures of looking how data propagates and is used, and also the techniques that enable us to measure privacy risk. Thank you all.
I have a few fire starter questions, but I would like to give the audience first the opportunity to ask questions. Yeah. All right. So tell me, you showed some privacy curves with acceptable risk thresholds. But if we look at a pragmatic way to it, how do you choose what is acceptable? So this was about the black line, I believe, as well.
I think that's a very tricky question. I think there's still a bit of discussion on one need to have between regulations, what I'm trying to achieve, and what I'm trying to get with my scenario. I think generally it's probably it can be dependent on the scenario and generally about how risky of an application is it. I would say there's probably an inherent different risk if I train a machine learning model on very sensitive attributes versus more like a general concept where like say health data inherently has a much higher risk than if we're training on more general things where the risk of re-identification might be not as bad as that. So there's still some exploration to do, but do you want to add anything to this?
Yeah, I think it's context dependent, yes. But the good thing is this. Now we have a tool and a defendable algorithm to quantify the privacy risks. It enables us to now talk about where the green and red regions are. But for certain image classification tasks, you have a different notion of risk that defines what you want to consider as your red line. For language model, it's another thing. For different kind of data, yeah.
Yeah, I want to make the link, the connection to the conformity assessments under the AI Act. I think such a visualization could be a really great way to explain what the model does and what the boundaries are. So it's like in essence, it could become part of a certification scheme as well, because it's about operational parameters things have been trained upon. Question for you.
Thank you for the presentation. I have a high-level general question. For using the privacy meter, I see it's like a GitHub. Is it easy enough to use for that if I'm an attorney, I work with a lot of data scientists and machine learning managers, am I able to give them this GitHub and say, there's instructions in here, you should be able to implement this yourself, you understand your models better than I can do? Is that part of, I think that's one of the gaps that I experience every single day. So I'd love to hear feedback, comments, how we bridge that gap. Thanks.
Yeah, very good question. The answer is yes. So it's a tool rather than some implementations of ideas. And there are very many tutorials on how to apply it in different types of models, different types of data. And actually there is a very active community there as well. So if your team actually wants to use it for a new setting, you can definitely get in touch. There's a Slack channel, and also the team is very active in addressing the issues. But yes, people are using it just from the GitHub. Yeah.
So just to add to this point, maybe the way to look at it is if for any machine learning tools, we have low-level access where we write Python code to train these models and we can integrate this code there and we have these opportunities. But on the other side, there's also high-level frameworks which allow me, I just give my data and I press a button and it fine-tunes my model and serve the experience. And I can integrate it there as well. And I think we just need to make sure that it's integrated at all levels of abstraction I'm willing to work and want to work.
Question?
Okay. Hi. Okay, it's a bit tall, but fine. I would like to thank, first of all, the presenters for their presentation, both of them. And actually, I would like to ask you if you could enter a little bit more into details about the trade-off between privacy and fairness, because I remember that some months ago I came across about some papers that were discussing differential privacy and how it seems not working the same. For example, if people in a data set have protected characteristics and so on. I was wondering if you can say a few more words about that, and if you know if similar studies have been carried out using other privacy enhancing technologies. Thank you.
Good answer last time.
Yes, so actually we do research on that. So you can check on research papers that we have written on this topic, and it totally depends on how we define privacy and fairness. So if we define privacy as leakage about privacy risk as leakage about individual data records in the training set, and we measure fairness as this discrepancy and differences between the accuracies of the model on groups of data points, when you partition the individuals into groups like blue people and red people, the accuracy gap between them, and you want to reduce that. Yes, they are in conflict with each other. So that notion of privacy is in conflict with this notion of fairness. Why? Because when you want to make the algorithm fair in the sense that the accuracy of the prediction of the model on group blue is the same as accuracy of the model on group red, while the size of group red is like 1/10 of group blue, when you want the accuracies to be the same, you are directly increasing the influence of individual data records in the small group on the model, right? Because naturally, this has like 1/10 of the influence on the model compared to the other group. You want them to have the same accuracy because otherwise these guys are ignored. So you increase the influence to make it fair. And when you increase the influence, each individual data record here would have 10 times more influence than the individual data record there. And that is something that in this membership inference attacks could be detected. So you stand out if you are a member of that group. No fairness, you are ignored. With fairness, you have huge influence. So that's one way to look at it. And also when you think about differential privacy, which tries to randomize and so on and so forth, it says every individual needs to be suppressed. So if you suppress every individual, then there are few in this group, and each individual of them have very small influence. Therefore, that group would suffer in terms of the accuracy. But if you change the definition of fairness, that trade-off might go away. And but that's a very good, challenging problem.
I have a question in that same vein, and this question is, should measuring the risk of re-identification be the main focus of privacy auditing?
I think measuring the risk of re-identification is one particular risk we can measure. We can do similar exercises with other properties, leakage risk. But we can also show that measuring the risk of re-identification covers a broader range of risks. For example, leaking of information is implicitly captured by measuring the risk of re-identification as well. Other risks are not captured. For example, revealing sensitive attributes about the whole population. This is definitely not covered, and we would need to design a different tool to measure, but we could report it in a similar way.
I want to speak to this issue exactly. I come from policy bubble. I'm just a lawyer, so excuse my ignorance in technical matters. But the key risk we are discussing now in the context of new legislation, especially for online platforms, but also AI systems, is a different risk. Is a risk that vulnerable features of humans, be that sensitive characteristics or not, can be exploited without identifying and singling out anybody. So the protection we would like to have somewhere from people like you here, from scientists, is actually the protection against use of these characteristics without. It does not matter in a way whether they leak or not and whether they are labeled or not. The idea would be how to prevent correlations being built on the basis of such features. And so far we have agreed in our policy bubble that it's a very tricky situation because the protection can only work when we demand companies to label people with these characteristics. And I wonder whether there is any progress in your field. Maybe there are any other solutions you are aware of. I know this is not the solution to achieve this result, this protection, without forcing people creating the system to label all sensitive features.
I think there's multiple questions. Let me try to tackle one part, and maybe you can augment on this one. So I think you touched on the risk of, can we protect correlations our model learns about our population? For example, I might learn that certain behaviors or I think there was an example by, if you have a certain shopping behavior, then you were pregnant, and there was a case where then advertisement for pregnancy tests were sent out to a person. Though that's a typical risk. I mean, if we train a model on this data, our intent is to learn these correlations. And even if you apply differential privacy, this risk will not be mitigated. Privacy is designed to expose general trends intentionally. So we have to revert back to other means. For example, what we can do, design an API to limit the access to the model. For example, you send in some data and you only get a certain request. And by controlling how many requests you can do to that API, we can make sure you can learn about something, maybe about an individual data point, about just for yourself, but not more, which you can abuse it. Now, that's a very vague answer, but I think it's a completely different type of mitigation and risk where you have to really think, how do you design the system around it?
Yeah, so I think this is a good answer, and let me complement this. the question is, whose fault is it when we have privacy laws? Okay, and in the case of data is given to an algorithm to construct a model, we blame the algorithm that now leaked information about individual data records in that set. It was not supposed to leak that, and that is what we are measuring here. In your scenario, it's the fault of data collection on the individual data that is going to be used for inference. It's not the fault of the model. The model's job is to learn the correlation. Now, this is a data minimization problem. When a user shows up, I should not have enough information about that user such that the accuracy of the model in predicting the remaining attributes is high. Okay? I should not ask enough, too much information. I visit a website, now you profile me. Then of course you would be able to using any simple model to predict the sensitive information. In the first place, the data collection must have been minimized. And there are ways actually to use inference algorithms, like simulate inference algorithms, to measure how to what extent, given what you have leaked or put on the table, I can infer the missing attributes. I can do imputation. Like, what is the risk of imputation? That could be measured in a different way, but that's somehow it completes the privacy risk spectrum.
Well, thank you. If you have a question, that will be the last one to wrap up.
Just a quick question.
Yeah, go ahead.
Well, thank you for the presentation. It was very, very stimulating. I do have a question, slightly off track if you want, which is considering both the scarcity of good quality data. According to Gartner, we're going to run out of them pretty soon, and on the other hand, all the issues that you tackled in the presentation, coming to privacy and so on, and considering on the other hand the quality of data produced by generative model, couldn't we just foster the use of synthetic data or fake data to train ML model instead of use real data, so that way bypass altogether the privacy issues? That's the question I wanted to comment from.
I think we both have something to say about it. But so it's essentially a question we tackled in a roundtable we hosted last year in December. The idea of synthetic data is, as you say, can we replace some of the real data with synthetic data? But how do we make sure our synthetic data reflects what we want to cover? So what we have to do when training synthetic data generators is apply privacy-enhancing technologies. As such, I see synthetic data generation as an application for privacy-enhancing technologies, not so much itself as a privacy-enhancing technologies. What we do is, in this aspect of data processing, training, post-processing, what Nigel talked about, we just push the problem a bit higher up in the chain. We push it up to the data processing aspect. We still need to make sure our synthetic data generation algorithm has been implemented in a privacy-preserving way. We inherit the same privacy utility trade-offs, if not even worse, than if you would apply differential privacy down the line. But what we gain is, after we did this, we need to worry less about it. So we can, for example, where we have an application where we need to look at the data to debug something, in this case, synthetic data generation could help to give us an intuition what is going on. Similarly, it can be very cumbersome to implement differential privacy correctly or other mitigations. By moving it up the chain, we give a bit more leeway down in the chain of the data scientists to do with the data what is required to do.
Okay, well, in closing, let me invite you to thank our speakers. Thank you very much.